Imagine trying to communicate a really complex, urgent thought. Like you need to tell a loved one something incredibly important, or maybe you just want to capture a brilliant, fleeting idea.
Right.
But your only method of getting that thought out of your head and into the world is by staring at a screen, pointing at letters one by one, using only the physical movement of your eyes.
Oh, wow. Yeah, it's incredibly slow.
It is slow, it is exhausting, and it is a wildly frustrating bottleneck for the human mind. But now I want you to flip that scenario. Imagine suddenly being able to type 22 words a minute completely effortlessly just by thinking about moving your fingers over a keyboard.
Which is just a massive leap. I mean, we are witnessing a fundamental shift away from external observation, like where a camera tracks a physical eye movement, toward direct internal neural decoding.
Exactly. And the implications for anyone who has lost their natural ability to communicate are, well, they're just staggering.
Absolutely staggering.
So our mission today is to unpack a groundbreaking 2026 report from Nature Neuroscience. It was led by Justin J. Jude and his colleagues, and the team developed a new intracortical brain-computer interface, or IBCI, that basically decodes attempted bimanual finger movements.
Basically allowing paralyzed individuals to type on a virtual QWERTY keyboard using nothing but their intention to move.
Right. And to really ground this deep dive, we need to look at the two individuals who made this clinical trial possible. We have participant T17, a 33-year-old living with ALS, and that resulted in tetraplegia and anarthria, meaning, he can't speak or move his limbs.
Right. The only remaining volitional movement is in his eyes.
Yeah. And then we have participant T18, a 48-year-old with a C4 cervical spinal cord injury. So he has no voluntary movement below his neck. Both of them have totally lost their primary avenues of communication.
Which is almost universally described as one of the most isolating aspects of severe paralysis. And, eye trackers do exist, but anyone who's used them knows they cause severe visual fatigue.
Oh, yeah.
They're prone to drifting. They require constant recalibration. So we really need a better bridge between the brain and the digital world.
Okay, let's unpack this, because I want to understand exactly how the hardware makes this new bridge possible. We're talking about microelectrode arrays. Where exactly are they placing these things, and what do they even look like?
Well, the researchers used Utah arrays. You can visualize them as microscopic beds of nails.
Ouch!
Yeah, right, but tiny. Each array features 64 tiny electrodes, roughly 1.5 millimeters long. And they're designed to penetrate the outer layer of the brain and just, listen to the raw electrical chatter of individual neurons.
And surgically, where are they going?
They're implanted into the precentral gyrus, which is the brain's primary real estate for motor control. Specifically, they targeted area 6-pen, the dorsal motor cortex, which is heavily involved in hand movement, and area 6V, the ventral premotor cortex.
Okay, got it.
In fact, T18 actually had 384 of these electrodes implanted across both hemispheres.
Wow. That is just a staggering amount of raw data being pulled from the brain. But having the hardware in place is, it's only half the battle. You need an interface that the user can actually conceptualize.
Exactly.
And the researchers use a really fascinating visual memory technique for this. So I want you, the listener, to picture playing a phantom piano.
That's a great way to look at it.
The participants don't physically move their fingers. The entire system relies on the raw intention to move them. And they're mapping 30 distinct commands.
Right, which perfectly aligns with the spatial layout of a standard keyboard. You have 10 fingers, and for each finger, the participant attempts one of 3 specific movements.
Okay, if I'm visualizing this right, movement 1 is extending the finger upward, which hits the top row of the QWERTY board, like the QWERTY keys.
Yeah.
Movement 2 is pressing straight downward, hitting the home row, the A, S, D, F, G. And then movement 3 is curling the finger inward to the palm, hitting the bottom row. So up, down, curl.
You nail it. Up, down, curl.
Yeah, but okay, I have a hard time buying the longevity of this. If someone like T17 has been paralyzed for years, wouldn't the motor pathways just degrade?
You'd think so, yeah.
How does the brain hold on to the blueprint of a finger curl that hasn't actually happened in a decade?
It is a phenomenal question. And the answer really highlights a core resilience in our neurobiology. The neural tuning, like the highly specific firing patterns of neurons associated with those movements, it remains incredibly stable even after the physical connection to the muscle is totally severed.
Wait, really? Just totally stable?
Yeah. When a participant simply attempts to move their pinky finger upward, Specific clusters of neurons in the motor cortex fire in a distinct, repeatable pattern.
Oh.
The brain doesn't discard the software just because the hardware is unplugged.
Yeah.
The motor cortex continues to simulate these actions with remarkable fidelity.
Okay, so if I'm synthesizing this first major hurdle for the listener, let's do a quick recap. Bullet 1, electrodes in the motor cortex are decoding 30 unique intended finger movements. And bullet 2, those up, down, and inward motions map perfectly to the 3 rows of a QWERTY keyboard.
Exactly.
So here's a question for you listening. If you close your eyes right now and pretend to type your name in the air, can you feel the distinct mental signals firing for each specific finger? Because capturing that tiny, isolated mental spark is exactly what this hardware is doing.
Yeah, but catching the spark is really only step 1, because the brain is incredibly noisy.
Right.
You have millions of neurons firing simultaneously to regulate breathing, process thoughts, and monitor the environment. Translating that, biological electricity into a clean digital sentence requires some serious computational power.
Which brings us to the algorithm. How do we actually get from a brainwave to a word on a screen? I know the computational heavy lifter in this deep dive is a recurrent neural network, or an RNN.
Yes.
How is the RNN filtering out all that background noise to find the actual typing commands?
Well, the RNN is constantly analyzing 2 specific features of the neural data. It looks at threshold crossings and spike band power.
Okay, threshold crossings. What's the best way to visualize that?
Imagine standing outside a crowded, really noisy stadium. You aren't trying to decipher the general roar of the crowd. You only care when a specific whistle blows loudly enough to cut through all that noise.
Ah, okay.
So the system establishes a voltage threshold, and every time a neuron's electrical spike crosses that specific amplitude, it counts as an event.
I see. And what about the spike band power?
Spike band power measures the overall energy of the high-frequency neural activity within a very brief window of time. So the RNN analyzes these 2 features in tiny continuous slices, or bins.
How tiny are we talking?
For T18, who had a faster typing cadence, the RNN evaluated a new bin of neural data every 120 milliseconds. And for T17, it was every 180 milliseconds.
So the AI is taking a snapshot of the brain's activity almost 10 times a second.
Exactly.
But I want to ask about the pacing. Because a major complaint about older BCIs was how robotic they felt, right?
Yeah.
The system would dictate the rhythm, like beep, imagine a letter, beep, imagine a letter.
Yeah, it was awful. It completely interrupted the natural flow of human thought.
So how does this new system allow the user to type at their own pace?
Well, that rigid pacing was a massive barrier. This new system incorporates what's called a CTC loss function, which stands for Connectionist Temporal Classification.
CTC.
Right. It elegantly solves the alignment problem between continuous, messy brain data and discrete, specific text characters.
So if I'm picturing how CTC works, is it sort of like a dynamic conveyor belt at a grocery checkout?
Oh, well, I like that. How so?
Like, if you pause to grab a sip of water, a traditional system might freak out or try to read the empty space as an item. But the CTC algorithm registers a blank token. It lets the empty belt roll by and just waits for you.
Yes, exactly.
Then, when you speed up and start placing items quickly, the algorithm adapts and processes them rapidly. It totally decouples the rigid clock of the computer from the variable timing of the human mind.
The conveyor belt is a perfect analogy. The RNN uses those blank tokens to separate distinct keystrokes. So a participant can attempt to type H, pause to think for a moment, which generates a sequence of blank tokens, and then rapidly attempt ELO.
Right.
The CTC algorithm collapses all that blank space and outputs the single intended word. But even with CTC, the raw output from the RNN isn't perfect. It is merely outputting the probability of a specific character.
So the AI is essentially guessing based on the brainwaves.
Right.
And that's where the researchers added a 5-gram language model, which was trained on the massive open web text-2 corpus, right?
Yes. And what's fascinating here is that it acts as an incredibly sophisticated error correction filter. The 5-gram model doesn't just evaluate the current predicted letter, it evaluates the entire sequence.
Like an ultra-smart autocorrect.
Exactly.
So if the RNN is, say, 80% sure the user's brain meant to type a T, but 20% sure it was an R, the language model steps in.
Yeah.
It looks at the previous letters and calculates that the sequence STAR makes perfect statistical sense in the English language, while STAT is highly improbable in that specific context.
Right. It forces the raw, noisy neural probabilities to just snap into grammatically correct English sentences.
Okay, so let's recap this algorithmic pipeline for the listener. Bullet 1, RNNs are analyzing brain spikes every fraction of a second. Bullet 2, the CTC allows for totally self-paced natural typing speeds.
Yep.
And bullet 3, a 5-gram language model cleans up the raw neural data into perfect sentences.
That's the pipeline.
So question for you listening. Think about how much you rely on your phone's autocorrect to fix your messy typing. What if that exact same autocorrect wasn't watching a screen, but was wired directly into the motor cortex of your brain, predicting the word you want before your fingers ever move?
And, the integration of that language model is actually the key to a massive debate within the field of neuroprosthetics right now.
Oh, what debate?
The choice between decoding a QWERTY keyboard versus decoding handwriting.
Yes, okay. I definitely want to explore this because it seems so counterintuitive to me. In 2021, there was a landmark study involving a participant known as T5, and he used an IBCI to imagine handwriting letters.
Right, the handwriting decoder.
He just thought about the fluid motion of writing an A or a B with a pen, and the speeds were incredible. I mean, handwriting feels so much more organic to the human brain than a keyboard. Why would researchers force this rigid, mechanical QWERTY layout into neural decoding?
Well, it comes down to a deep analysis of how errors propagate in these systems. And this is arguably the most brilliant insight of the whole paper.
Really?
Yeah, if we connect this to the bigger picture, it is all about the synergy between the type of human error and the AI language model you just discussed. In handwriting decoding, errors naturally occur between letters that share similar physical trajectories.
Oh, like writing an R and an N. The loops and the downward strokes are incredibly similar, so the neural commands would naturally just overlap and blur together.
Exactly. And the same overlap happens with vowels, like A, E, O, U.
Right.
The shape representations in the motor cortex can easily be misinterpreted by the decoder.
Okay.
But the real problem is that in the English language, vowels are highly interchangeable within words.
Oh, wow. I see the trap. If the user intends to write B-A-D, bad, but the shape error causes the computer to think it's B-E-D, bed.
Right.
The language model looks at bed, confirms it is a perfectly valid English word, and just leaves it uncorrected. Shape errors create valid but completely wrong words, which bypasses the autocorrect entirely.
Exactly. It's a huge blind spot. But the QWERTY keyboard completely circumvents this vulnerability. On a keyboard, errors aren't based on the shape of the letter, they are spatial.
Ah, spatial errors.
Yeah. If your intention wavers slightly while aiming for the T key, your neural activity might slip and trigger the adjacent finger movement, resulting in an R.
Which happens to me physically all the time on my phone.
We all do it. But notice what happens when you swap an R for a T in English. It usually creates absolute gibberish. If you try to type the word there, T-H-E-R-E, and you hit the R instead of T, you output R-H-E-R-E. The language model flags that instantly because here is not in its vocabulary.
That's so smart.
It checks the keyboard map, sees that T is spatially adjacent to R, and automatically fixes the typo. The spatial layout of QWERTY forces errors into nonsensical patterns that an AI can easily catch and correct.
That is incredibly clever. They basically engineered the interface to produce the specific kind of error that AI is best at solving.
Exactly.
So how fast are we actually talking here with this optimized system? Like, what are the real-world results?
The results are historic. Participant T18 achieved an astonishing 110 characters per minute.
Wow.
Which translates to roughly 22 words per minute with a word error rate of just 1.6%.
That is wild.
To contextualize that, it is 81% of the typing speed of an able-bodied person in his age group using a smartphone. And participant T17, despite having fewer electrodes and advanced ALS, still hit 47 characters per minute.
I mean, that is life-changing velocity for someone locked in.
Truly.
So to pull this section together for you listening, bullet 1, handwriting BCIs create shape errors that confuse autocorrect. But bullet 2, QWERTY BCIs create spatial errors that are easily fixed by language models.
Yep.
And bullet 3, this synergy is what allows for 22 words per minute at near perfect accuracy. So, question for you. Have you ever sent a text full of massive spatial typos, maybe a rogue ducking, and your phone just magically formatted it into a coherent sentence?
We've all been there.
Right. That exact spatial forgiveness is what is giving paralyzed patients their voice back in real time.
But, speed and accuracy in a controlled lab setting are really only part of the equation.
Sure.
For this technology to actually reach patients' homes, It has to be practical to use daily.
Which has historically been a massive roadblock. I know older BCI devices were notorious for requiring hours of exhausting calibration. A patient couldn't just wake up and start typing.
No, not at all.
They had to run through endless mental drills to set a baseline for that specific day every single day.
Right, because the brain's background electrical environment fluctuates, and the electrodes themselves actually undergo microscopic shifts.
Ah, that makes sense.
However, because the QWERTY layout relies on highly familiar, discrete finger movements, the algorithm learns the user's specific neural patterns incredibly fast. For T18 to achieve a highly usable 7% word error rate, he only needed to type 30 calibration sentences.
Only 30.
Yeah. Compare that to the handwriting BCI, which required more than double the calibration trials to reach the same accuracy.
Okay, here's where it gets really interesting, though. Looking at the anatomical data here for participant T17, this completely defies the textbook biology I learned in high school.
Oh, the bihemispheric data.
Yeah. T17 only had electrodes implanted on the left side of his brain. Just 128 electrodes, with 0 hardware on the right hemisphere. And we are always taught that the left brain controls the right hand and the right brain controls the left hand. How is it physically possible they decoded his left hand movements from the left hemisphere?
It is a profound physiological finding. The researchers were able to decode movements from his left hand with 84.3% accuracy, which is nearly identical to the 86.1% accuracy for his right hand.
That's crazy.
It proves there's a redundant bihemispheric representation of bimanual finger movements.
But why? Why would the brain dedicate resources to mapping the left hand in the left hemisphere if it doesn't directly control it?
It really comes down to the evolutionary necessity of bimanual coordination. Think about a complex task, like opening a jar.
Okay.
Your right hand twists the lid, but your left hand has to apply the exact opposite stabilizing force on the base. If the two hemispheres were completely siloed, the communication lag would make fluid, coordinated tasks nearly impossible.
Ah, I see.
So the left brain intimately tracks what the left hand is doing, so it can perfectly calibrate the right hand's response. The neural blueprints are shared across the divide.
Wow. It's like the brain has a built-in backup system for motor control.
Exactly.
And speaking of stability, how does this system handle signal drift over time? Like, do they still have to recalibrate those 30 sentences every morning?
Incredibly, no. The researchers found that even without any daily recalibration, T18's decoder maintained a highly functional 12% word error rate after a full 7 days.
7 days with no resets.
Yeah. The neural representations of these specific up, down, and curl movements proved to be extraordinarily stable over time.
Okay, so to synthesize our final technical look here. Bullet 1, only 30 sentences are needed to train the AI to your brain. Bullet 2, a single hemisphere of the brain contains the blueprints for both hands. And bullet 3, the decoder remains stable for days without needing a software reset.
It's just phenomenal.
So, question for you listening. If your left motor cortex holds the mapping for your left hand, what other redundant backup systems might your brain be hiding?
I mean, it fundamentally changes how we view recovery and rehabilitation. The hardware might be damaged at the spinal cord, but the software in the brain is not only intact, it is robust, redundant, and completely ready to be tapped into.
As we step back and look at this entire deep dive, the magnitude of what Justin J. Jude and his team have accomplished is just breathtaking.
It really is.
Moving from the agonizing, fatiguing process of staring at a screen waiting for an eye tracker to typing 22 words a minute just by letting your mind perform a familiar action. That is not just a medical upgrade.
Yeah, it's a paradigm shift.
That is the threshold between merely surviving an injury and truly actively engaging in the digital world. It is the ability to argue, to interject with a joke, to write a letter at the speed of human thought.
And, we are really only at the beginning of the curve. The authors point toward the integration of large foundational models.
Like GPT.
Yes. This raises an important question. If a localized 5-gram language model can perform this level of error correction, imagine integrating a massive transformer model trained on billions of parameters.
Oh, wow.
We are looking at a near future where 0 daily calibration is required right out of the box. The BCI will simply update itself silently in the background while the user free types.
And that leads me to a final provocative thought for you, the listener, to mull over. This technology essentially skips the physical body, connecting human intention directly to a digital interface. Right now, we are asking patients to imagine a physical QWERTY keyboard because, Well, it is what we all know.
Yeah.
But if the interface is no longer constrained by the physical limits of human fingers or vocal cords, what happens when we start designing virtual keyboards that don't just type words? What if they execute complex macros, or write code, or transmit abstract emotional states directly from our motor cortex? Where exactly is the boundary between the human mind and the digital world when the keyboard becomes entirely invisible? Think back to where we started, that slow, exhausting process of pointing with your eyes. We've just crossed the threshold into a reality where your thoughts are the only keys you will ever need.